Assalamualaikum, my name is Megat Najmudin. So I will start the presentation with introduction. So our experiment focus on dynamic systems and control using Matlab and Simulink. We explore the design interfaces of P, PI and PID controllers using the Ziegler Nichols method and PID tuner in Simulink. Our objective was to achieve optimal transient responses. We share insights and lessons learned in this engaging exploration of control engineering.
Hello, my name is Mohamad Aiman, and I will present to you the methods that we use for this assignment. So, in this assignment, we will use both manual calculation and Matlab simulation to design a P, PI, and PID controller for a closed-loop system with appropriate system requirement for transit response by tuning controller using Ziegler-Nichols method. The Ziegler-Nichols method is a very popular method for tuning P, PI, and PID controllers by zeroing the integral and differential gains and then raising the proportional gain until the system is unstable. The value of Kp at the point of instability is called Kmax. The oscillation frequency is called Fo. The method then backs off the proportional gain a predetermined amount and sets the integral and differential gains as a function of Fo. The P, I, and D gains are set according to table 1. So, as you can see, the table 1 is the settings for PID gains according to the Ziegler-Nichols method. Now then, once the manual calculation is done, we will run a simulation using the built-in Matlab simulation tool called Simulink. And with using Simulink, we can simulate and illustrate complex mathematical equations using various tools that are available.
Assalamualaikum. Now I will discuss about the result and discussion for our group. Firstly, the result using calculation using Ziegler-Nichols method. Firstly, we need to identify what is our transfer function, which for our group is GS equals to 6 over 4s power of 2 plus 2s plus 6. Then we need to make the transfer function equals to 0, which using formula which is transfer function plus 1 and times with KCU. We will get this equation, and then we just throw this away to the right side, which is equals to 0, and we get the 4s power of 2 plus 2s plus 6 plus 6 KCU. Then after that, this equation will substitute S equals to J omega. From here, we need to make two equations which are real point and imaginary point. From this imaginary point, we can find KCU, which is KCU equals to 4 omega power of 2 minus 6 over 6. We will substitute omega with square root of 2, which we will get 1 over 3. Then we can find PU. The formula for PU is PU equals to 2 pi over omega. So substitute omega with square root of 2, we will get 4.4. After we get KCU and PU, we can find KC, TI, and TD using this Ziegler-Nichols method table, which is KCU over 1.7 we will get KC, which is 0.196. For TI, we can get by PU over 2, which we will get 2.22. And lastly is the derivative TD, which will get PU over 8 equals to 0.555. From here, our PID is 0.196, 2.22, and 0.555. That's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hazimi bin Ahmad Maiza, and my metric number is PE 220-160, and I will continue the presentation on the simulation of Simulink. first, for the first system, we have this open loop. We have a step here, and this transfer function called transfer function 1 or TF1, and we have output scope 8 here. So let's move to the command window. And then in command window, we are going to type the transfer function equation, which is TF1 is equals to transfer function in bracket 6 comma open bracket 4 2 and 6 close the bracket. So in command window, we already register the transfer function 1, which is 6 over 4s squared plus 2s plus 6 into the word space. So what we need is to plot the system response. To do that, we simply type step in bracket transfer function 1. So we have this figure, and then this is our step response for open loop. Next, we're going to right click and click on rise time, click on settling time, transient time, and steady state. Alright, so in this step response, we have peak amplitude at 1.52, maximum overshoot is 51.9% at 2.58 seconds. The rise time is 0.989 and the transient time is 40 seconds. The system is steady at final value of 1. Or if we want to get the step info without plot the step response, we have to input s equals to step info of the system transfer function 1, and it will show us the rise time, the transient time, settling time, minimum settling and maximum settling, overshoot, undershoot, peak and peak time. So this is for the first one, transfer function 1 for the open loop system. Now we're going to move to the second one. Okay, now we will move to the closed loop system. So in this system, we have this transfer function here and this controller here, which is p-type controller. So in transfer function 2, we already input the numerator and the denominator coefficients based on the transfer function 1. So basically, the transfer function in this simulation is the same. The only things that make it different is the controller type. So click OK. What we're going to do next is we click on this P controller, and then we're going to input the proportional gain value based on the Ziegler method table. So in the Ziegler method table, we have 0.167. Then we are going to click OK, click run, wait for a second. Then we're going to click scope. So this is our graph for the system using p-type controller. What we're going to do next is we're going to click again the p controller here. As you can see, at here we have tune button. But first we need to select tuning method to transfer function base PID tuner app. So we're going to hit tune. Wait for a second for the plan to loading. And then this is our step response. The dotted line here is the block response that we insert the p value, which is 0.167, and this straight line here, this full line here is the tune response, which is the PID tuner is automatically tune our response to get the desired value. So we click the show parameter here. Alright, I will expand. Okay, so we have tune and block. So the tune is automatic, and the block is what we put in the P controller. So when we put 0.167, the automatically tune is at 3.1337. So at here we already know the rush time, the settling time, the overshoot, and the peak, as well as gain margin, phase margin, and closed loop stability. For the both block and tune, the system is actually stable. What makes it different is the rise time value, the settling time, the maximum overshoot percentage, and the peak response. So we close this and close this, and then we're going to move to the second one, which is using the PI controller. So same, the transfer function is the same throughout this simulation, so we're going to click OK. At the PI controller, we're going to put the proportional gain as well as the interval gain value based on the Ziegler Nichols method. So 0.152 and 3.70. Click OK. Save, we click on run. Wait for a few seconds, then we're going to click scope. So this is our graph for the system using PI controller. Click on the PI controller again. Make sure the transfer function base PID tuner app is selected and click on tune. So this is our tune response for the system. Click on show parameters. I will expand this. Alright. Notice that we don't have block parameters, we only have tune parameters. So in tune parameters, the proportional is set to 0 because it doesn't use the P controller. It uses the I value only, which is at 0.21849. So this is the tune response. The system is stable as well. So we're going to click close. And then we're going to move to the last part, which is the system using PID controller. So make sure that the transfer function is the same. Click on OK. What we're going to change in PID controller is based on the Ziegler-Nichols method as well. So P is 0.169, I 2.22, D is 0.555. So we're going to click OK and click run. Wait for a few seconds and we're going to click on scope. So this is our graph for the system using PID controller. The filter coefficient and value is default at 100, so we're going to leave it there. And then click on tune. So this is our step response for the system using PID controller. Notice that both PI controller and PID controller produce exactly the same graph response, but it's actually not the same at all. So we're going to click on show parameters. Notice that the P value and the D value is set to 0 because it uses only I value, which is at 0.23967. Sorry, 0.23667. So this is the tune parameters for the rise time, settling time, overshoot, peak, gain margin, phase margin, as well as the closed loop stability. So the system is also stable. What makes it different is the overshoot percentage, which is significantly lower than P controller and PI controller. Nevertheless, the open loop system. So in conclusion, using PID controller, we have minimized the overshoot, maximum overshoot percentage, as well as the settling time. So the system will get steady state in less time when we use PID controller regarding to the simulation. So that's all for me. I will pass this presentation to the next presenter. Thank you very much.
Hello, my name is Muhammad Akif bin Muhammad Shaid and my matrix number is DE220140. I'm going to continue the discussion by explaining about the result and the discussion of the project. So based on the first result, which is open loop system that has begun by using the PID tuner by Simulink, by using the estimated gains values, gain by using the Ziegler-Nichols method, we gain this transient response. And as you can see from the right hand side of the screen, it shows the result in numbers. So as you can see from the settling time, it shows a low number, which is about 13.9 seconds, and the overshoot percentage is quite high, which is 51.87%. That is by adding the P controller to the system becomes a closed loop system, and by simulating using the PID tuner, we gain this result. By observing the transient response, the system has become more stable, but not as stable as we want to be compared with the previous result. So as you can see from the results, this is where we put the P gain value that has begun by using the Ziegler-Nichols method. And as you can see from the result, the settling time has increased to 50.4 seconds, while on the other hand, the overshoot has increased also to 72.8% to be compared with previous result. So by adding I to the system, we gain PI controller system. So this is the transient response that has begun by using the PID tuner, which is more stable to be compared with previous result. So by observing the result in numbers, the settling time has increased to 18.2 seconds, and the overshoot percentage has decreased greatly to 0.318%. And by using the PID controller to the system, we gain a more stable result by observing the transient response. As you can see, the settling time has decreased a bit to 18.1 seconds, and the overshoot becomes 0.927%, which is a good combination of low values of settling time and overshoot, which means that the system will perform with good performance. So based on the result that we have gained, we can conclude that Ziegler-Nichols method and PID tuner by using Simulink should be used together to achieve the most optimal and optimized result. As you can see, we use both Ziegler-Nichols and PID tuner method together to achieve this result. And what do I mean by that is that by using the Ziegler-Nichols method, we can produce the initial estimates value for the PID gains for the beginning process of tuning. And the next part is by using the PID tuner by Simulink to refine and optimize the gains by using the fine-tuners feature that is included in the Simulink. So that's all for the discussion.
So this is our sustainable development goals. What we get for number 8 is decent work and economic growth. Control engineering and system modeling skills can contribute to SDG 8 by boosting productivity, generating jobs, and enhancing workflows across industries, ultimately promoting sustainable economic growth. For the next, Number 9, industry innovation and infrastructure. The experiment promotes a system modeling control strategies and Matlab Simulink tools, advancing SDG 9, fostering innovation, building resilient infrastructure, and promoting sustainable industrialization by teaching people these competencies. The last one, number 11, sustainable cities and communities. The experiment contributes to SDG 11 by developing skill for sustainable cities and communities, focusing on effective control strategies for complex urban systems like traffic and energy management. So for the summary, our experiment successfully explored dynamic system and control strategies, highlighting threats of and feedback impact. It refined Matlab Simulink skills and underscored the importance of systematic approach for optimal performance. So that's